Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on linear control system. Today we will discuss lecture number 4 of this course. In lecture number 3 we discussed the mathematical modeling of linear time invariant systems which involve differential equations. So the generic model of differential equation model for an LTI system consists of derivatives of the output on the left hand side with constant coefficients a1 a2 up to so on an. Notice that the coefficient of the highest derivative of the output is 1. That's a standard. And on the right hand side you have derivatives of the input with coefficients b0 b1 and up to so on bm, and for causality m is less than or equal to n. And then we discuss the transfer function model for LTI systems, which is basically can be derived by taking Laplace transform of this differential equation under zero initial conditions. The good thing is that this coefficients of the derivatives of the input becomes the coefficient of the numerator polynomial, and the coefficient of the derivative of the output become the denominator, the coefficients of the denominator polynomial in the Laplace transform. For details you can revisit lecture number 3 of this course. Then we discussed impulse response, which can be derived either in the lab or by taking inverse Laplace transform of the transfer function. Well, in the lab it is difficult to create an ideal impulse, but practically you can also take the step response, and then impulse response is basically the derivative of the step response. Then why the significance of impulse response is that you can calculate the response to any input u of t by using the impulse response. You just have to convolute the impulse response with the desirable input, and then you can get the corresponding output for that input. Then there is step response, which is the Laplace inverse of gs over s, and it is also the Laplace of the derivative. So the transfer function is the Laplace of the derivative of the step response. The derivative of the step response is same as the impulse response, and gs over s is 1 over s in Laplace domain is the representation of integration action. So basically step response is the integral of impulse response, and by fundamental theorem of calculus impulse response is the derivative of the step response. Frequency characteristics, we also discussed that briefly, but the more detailed discussion will be in the lectures that discuss Bode plot and Nyquist plot towards the end of this course. And let's move on to lecture number 4. The contents of lecture number 4 is the state space model. That is the last of the 5 ways to model LTI systems. In state space model we have in the transfer function model we have the input and the output representation, whereas in the state space model the difference is that from the input to the output we have some intermediate internal variables of the system involved. So in the state space model it is basically the internal model of the system, which is more than just the output and the input. So there are some dynamics of the system represented by the dynamics of variables called state variables, and then state variables are involved in the output as well. So you can think of it as output is in some cases could be one of these variables, and in general output is a linear combination of the input and the state variables. State vector x is a set of internal variables called the state variables of the system. In order for the x to qualify as the state vector, The value of x along with the value of u at any given time must be enough to uniquely determine the value of the output. So if you look at any dynamical linear time invariant system, there can be many variables involved in that system. For example, take a car. So in the car there are different variables. For example, the speed of the car, the position of the car, the direction of motion of the car. So if you combine direction of motion with the speed, then it becomes the velocity of the car. And similarly, there could be some other variables. For example, how far you have pressed the steering, how far you have pressed the gas pedal of the car, the gear is also another variable. Then temperature of the car could be also another variable. Then amount of water in the carburetor, that's also variable, because you know that water changes, the amount of water changes with time as the car is moving. So there are so many variables. But in control systems, when you are solving some sort of a problem, you're not always concerned with all of the variables. Then the question is, how many variables should we consider? So this is the answer of this question. So state variables is the amount of variables that if you come, so every variable provide you some information about the system. Okay, so if the values of the variable combined with the value of the input is enough to uniquely determine the output, then that bunch of variables can be qualified as state variables. If the state variable information is not enough to uniquely determine the output when combined with the information of the input, then it does not qualify it as like a set of state variables. So in the state space model, output is represented as a linear combination of the state variables and the input. You can see here that y is equal to cx plus d, where c and d in LTI systems, c and d are constant matrices and a and b are also constant matrices. In time varying systems, these are functions of time, but time varying systems are not part of this course. In above state space model, d is usually 0. Moreover, the output in many cases is equal to one of the state variables. So there are some, when we go into the practical systems, these are not as complex as the general form. Most of the physical systems that we deal with in control systems nowadays, they don't have this feed through term where y is directly dependent upon the u. But anyways, this model allows for y to be directly dependent upon u. Then let's look at some examples how we can develop state space model from the transfer function. So consider the following LTI system. This is the third order transfer function 1 over s cube plus 3s plus 4, and now the corresponding differential. So in order to find the state space, you first have to convert well, you don't have to convert it into differential equation, but here, because I'm trying to teach you how the state space work, or how you can develop state space model from scratch, so it is more instructive to convert this into differential equation. So we convert this into differential equation by taking inverse Laplace transform. The denominator polynomial becomes the differential equation for the output. S cube becomes y triple dot, 3s becomes 3y dot, 4 becomes 4y, and this 1 becomes 1u. So that is how you get the differential equation for transfer function. We have already discussed this in the previous lecture. Now we develop the state space model, and this will involve 3 steps. Step number 1, define the state variables. Step number 2, derive the state dynamics. And step number 3, write the model in matrix form. So let's go through all of these steps and see how this model will be developed for this. So moving on with the example, we have this transfer function, and we have so far converted it into differential equation, and now we go to the step number 1. Now defining the state variables, there are many ways of doing that. One of the ways that we will discuss in this lecture is basically that involves defining the output to be equal to the first state variable. So the first state variable in the system that we define is the output of the system. Then the second variable, state variable, is defined as the derivative of the output of the system. As we see that the dynamics of the system that we have, it involves the derivative of the output, and basically it involves up to the third derivative of the output. So we also define a third state variable, which is the double derivative of the output. Now we do not define any further state variable, which we do not define x4 equal to y triple dot. Why? Because defining the three variables is enough for our purposes. We don't have to have more than three variables, otherwise it will be like non-minimal realization of the LTI system. As I discussed in the previously, that you can have as many variables as you want, but how many variables do you really need? So these three variables will be enough to uniquely determine the output. Actually, the output will always be determined from x1 alone. So this in that sense it over qualifies. But why do we need then x2 and x3? Because in order to capture the whole dynamics of the system, we have to capture up to the triple derivative of y. That is why we need x2 and x3. So derivative, then we derive the state space dynamics. So dynamics will be easy because of the way we have defined our state variables. That will help us in deriving the dynamics. So the dynamics of the first state variable x1 dot, that will be simply y dot, which is we have already defined it as x2. So x1 dot is equal to x2, that is the dynamics of x1. Then x2 dot is equal to y double dot, as x2 is y dot, then its derivative will be y double dot, and then that has been already defined to be equal to x3. So these two dynamics are very straightforward. Then x3 dot is y triple dot, and y triple dot will be derived from this equation. So if you look at this equation, y triple dot is equal to u minus 3y dot minus 4y. So this we have written here, u minus 3y dot minus 4y, and this is equal to u minus 3x2 because y dot is x2, and 4x1 because y is x1. So this is how x3 dot is equal to u minus 3x2. So this is the dynamics of x3. So we have derived the dynamics of all three state variables, and you can easily see that these dynamics fully capture the dynamics of the system represented in the differential equation or the Laplace transform, because it captures up to the y triple dot. Then so far we have x1 dot equal x2, x2 dot equal x3, and x3 dot equal u minus 3x2 minus 4x1. The final step is to rewrite these dynamics into the matrix form. So if you write this into x dot equal ax plus bu, y is equal to cx plus du. I can use the capital B here because in the previous slide the B was capital, so it's just a typo. So x dot is equal to, x will be the state variable vector, so this will be x1 dot, x2 dot, x3 dot, and since x1 dot is x2, you can write it as 0 times x1 plus 1 times x2 plus 0 times x3 plus 0 times u, and then x2 dot is x3, so it is 0 times x1 plus 0 times x2 plus 1 times x3 plus 0 times u, and x3 dot is u minus 3x2 minus 4x1, so it is minus 4 times x1 minus 3 times x2 plus 0 times x3 plus 1 times u. So that is how you convert this into matrix form. And finally y is equal to cx plus du. D is 0 in this case, so c will be like y is equal to 1 times x1 plus 0 times x2 plus 0 times x3. So this is how you write this in the matrix form. Next, the state space representation of LTI system is not unique. Basically, this way of finding state space representation from the transfer function, this is the controllable canonical form. There are some other canonical forms of state variables. There are some state variable representation can also be non-minimal, and non-minimal means that if you convert it into the transfer function, the order of the system may reduce because of pole zero cancellations, and it has some other implications which we don't have to discuss at this point. So state space representation of an LTI system is not unique. There might be other. So for example, we could define x1 is equal to 3y or y plus 2y, or y plus something, some other thing. We could have defined x3 to be equal to y. There are so many other ways of defining state space for a given LTI model. So one could define the states in a different way, though there are many different ways. So this particular way that I have taught you, that is for developing the controllable canonical form of the state space model. So let's look at another example. Consider this following transfer function, 5s plus 2 over s cube plus 3s plus 4. So the denominator is the same as the previous example, but the numerator now has the s term in it. So there will be, if you convert it into differential equation, there will be u dot. So remember that there is no u dot allowed in the state space model. So we have to be careful here while converting this into the state space. The method that we learned in the previous example will be applied here, but not in a very straightforward way. What we will do is that if we were to develop the state space model, then this will involve 5 steps instead of 3 steps. Step number 1 will be break the numerator and denominator as a series combination. So we can write this as this term multiplied by this term. So this multiplication, if you convert it into block diagram, that will be the series of 2 blocks. Derive the state space dynamics for the denominator transfer function. So derive the state space for this part alone, that we have already done in the previous example. And then derive the equation of the final output using the output of the denominator transfer function and the dynamics of the numerator transfer function. This will be more clear after we actually do the example. And step 4 is write the equation of the final output in terms of state variables, and then write the model in the matrix form. So let us see how we execute these steps. So for example, in this case, we will have this denominator transfer function, this intermediate output, then numerator transfer function, and the actual output of the system. So the actual system is from this u to this y, and we have converted into a series combination of 2 systems, where we have introduced an intermediate output which we will get rid of in the final derivation. So define the state variables of the denominator transfer function. So in order to do that, we just have to look this part of the system. So we just have to consider this as the input and this as the output. Then x1 is equal to y bar as we defined before, x2 is equal to y bar dot, x3 is equal to y bar double dot, and then the dynamics will be x1 dot is equal to x2, x2 dot is equal to x3, x3 dot will be u minus 3x2 minus 4x1, as we did before. So this part is exactly same as our previous example. So all of the logic used is the same as we used in the previous example to get this equation. Now the next step is to derive the equation of the final output using the output of the denominator transfer function and the dynamics of the numerator transfer function. So in order to do this, what we will do is, so if you look at this transfer function, this has a denominator equal to 1. So input y bar will be simple y bar, and at the output you will have 5y dot plus 2y. Numerator is for the output, and denominator is for the input. So we will have y will be equal to so when y bar goes through this, then it will be equal to 5y bar dot plus 2y bar. So if you convert this, if you take the transfer function y over y bar equal to 5s plus 2, then y bar will go to the other side. So let me just write this. So y over y bar is equal to 5s plus 2. So that is the meaning of the transfer function. So this y bar will go to the other side and multiply with 5s plus 2, and when you convert it into time domain, the s will become the derivative. So 5s into y bar, that will become the 5y dot, and this 2 constant will become just a simple y bar by taking the inverse Laplace. So then we write the equation of the final output in terms of the state variables. So remember that this y bar is x1 and y bar dot is x2. So y is actually equal to 5 times x2 plus 2 times x1. So this was the additional information that we need to obtain, for which we just break down this system so that we can use the previous example method for this part, and just simple algebra plus Laplace transform for this part. And then after we get this equation, now we are ready to write down our system in terms of state space. So remember, now this y bar is now completely out of the equations, because x1 dot is x2, x2 dot is x3, x3 dot is u minus x3, x2 minus 4x1, and now y is equal to 5x2 plus 2x1. But internally, if you are looking for what is the meaning of x1, then in this case the x1 is some internal state variable which is y bar, but what you're really concerned about is what is the output. So output is a linear combination of two states here, so it does not matter what x1 alone physically means. What matters is that what does this linear combination physically means. So this linear combination physically means the physical output of the system. So rewrite the above dynamic in the standard state space matrix form. So if you rewrite this, x1 dot is 0 times x1 plus 1 time x2 plus 0 times x3 plus 0 times u, as similar as before. This whole thing is exactly the same as before. The only difference is, instead of y being equal to 1 times x1 plus 0 times x2 plus 0 times x3, this time y is equal to 2 times x1 plus 5 times x2 plus 0 times x3. So that's the only difference when you have derivatives on the input side in the transfer function or the differential equation. So I hope that these two examples have clarified how you convert transfer function into state space. Once the concept is clear, how the states are defined in every case, now you can also practice, so this is the final generic form. You can also practice direct conversion as well. So if you have this type of differential equation, you can directly write the state space here. So you can all see that in the state space matrices, the B matrix will always be all zeros and a 1 at the end. A matrix will be all zeros except the diagonal above the main diagonal will be all ones, and the last row will be the minus an minus 1 and up to so on minus a1, these coefficients in the reverse order with negative sign. And y will be the coefficients of the derivatives of the input in the reverse order, and these since m is less than equal to n, so if m so these zeros will be the filling zeros. For example, the number of zeros here will be m minus n minus 1. So if m is 3 and n is 4, then you don't need any of these zeros. So if the difference between m and n is more than 1, then you need these zeros. For example, if m is 1 and n is 3, then you will need 1 0 here. Yeah, 3 minus 1 is 1. So g of s is, so you can also convert state space back into transfer function by using this formula. G of s is equal to c times si minus a inverse b. We will also see the example of this. Since state space may not always be in this form, so you may not be able to directly convert it back to transfer function without any calculations, but you know, if any generic state space is given to you, you can always find the transfer function using this formula. So let's look at another example of conversion of this LTI system into state space. So for example, this will have a transfer function 2s square plus 9s plus 6, and this comes from the numerator. From the right hand side of the differential equation comes the numerator of the transfer function, and from the left hand side of the differential equation comes the denominator of the transfer function. And similarly, you can write state space directly for this system, because you can write the coefficients here. 1 will become minus 1, minus 3 will become plus 3, this 5 will become minus 5, and this will be all zeros and 1 at the end, and this will be this 6 will be as it is, this 9 will be as it is, this 2 will be as it is. So there m is 2 and n is 3, m minus n is 1, so we don't need any filling zeros in this example. So here you can see that these coefficients in the differential equation are same as the coefficients in the transfer function, and in the reverse order with negative sign in the state space matrix. Similarly, these coefficients on the right hand side, these are the same as the coefficient in the numerator, and in the reverse order in the state space. So another example, you can see here that y triple dot plus 5y is equal to u, 4y is equal to u. That's transfer function will be 1 over s cube plus 4, and then you can convert it into state space like this. So here this numerator 1 comes here, and since the difference is so here m is equal to 0 and n is equal to 3, so m minus n is 3, 3 minus 1 is 2, so we need 2 filling zeros. So coefficient of y double dot is 0, so s square term here is 0, and coefficient of y dot is 0, so s term in the transfer function is 0, so that is why these two terms are also 0. Now another example, y triple dot plus 2y dot plus 3y is equal to 8u dot minus u, converted into transfer function. Similarly, this 3 comes at minus 3. There is no coefficient of s, so here as a 0. This 2 comes at minus 2, and this the last one in the, and this is the minus 1 comes as it is here, and 8 plus 8 comes here. And since this m is equal to 1 and n is equal to 3, m minus n is equal to 2, and 2 minus 1 is 1, so there is 1 filling 0. So these are the examples, and you can also convert, as we discussed before, you can convert state space into transfer function. This slide will show you how you can convert state space into transfer function using the Laplace transform under zero initial condition. So if you take the Laplace transform of this differential equation, this will be derivative becomes s times x of s is equal to a times x of s plus b times u of s, and y will be equal to c times x of s plus d times u of s, and the one will imply that s times x of s minus a times x of s is equal to b times u of s. And now we take x of s as common, and then x of s becomes si minus a inverse b times u of s. And if we substitute 3 into equation number 2, then y is equal to c into si minus a inverse b times u of s plus d times u of s. And if you take u of s as common and then take it to the left hand side. This is the transfer function, and transfer function is C into Si minus A inverse B plus D in general, and when D is 0, then this is just C into Si minus A inverse B. So this is how we derive this formula of conversion of state space from the conversion of state space into the transfer function. And now we look at the example. For example, if we are given this state space, notice that this state space is not in the standard controllable canonical form, so you cannot convert it back to transfer function just by looking at the coefficients. So you have to use this formula, G is equal to C into Si minus A inverse B. So here in this case, C is 136, S is just the Laplace variable, I will be the identity matrix of 3 cross 3, which is the same size as the size of A. This is A. We'll take the inverse of it and multiply it with B. So notice this, after all this multiplication, this whole term will be just a scalar. So this is 1 cross 3, 3 cross 3, and then this is 3 cross 1. So if you multiply all three of them, this will be 1 cross 1. So transfer function is basically a scalar complex number. And then we do these calculations. We multiply S into the identity matrix and subtract this A matrix from this Si, so we'll get this matrix. And then from here we can just first of all deal with this inverse. So we solve the inverse like we take the adjoint of this matrix divided by the determinant of this matrix. So if you take the adjoint of the for taking the determinant, you just pick one of the rows or one of the columns. This is easy column, so S minus 2 into its cofactor plus 3 into its cofactor, and that will be the determinant. It will be S cube minus 3S square minus 27S plus 103. And now the adjoint will be, you have to replace every term, you replace S2 with its cofactor along with the sign, and replace every element with its cofactor and take the transpose. That will be the adjoint. And once you divide the adjoint with the determinant, that will be the inverse. And now if you look at we just multiplied this adjoint with the B matrix here 146, and then we get this matrix here. This is now we take this one into so this was our original equation, Si minus A inverse into B, and here is C into Si minus A inverse into B. We have multiplied the adjoint of this with the B matrix, so we have this basically is this is the determinant, which is a like scalar term, so it comes out, and this is the multiplication of adjoint of this inverse multiplied by this, and we finally multiply this row vector with this column vector, and then we get this 49s square minus 373s plus 680, and this denominator comes down as it is. So this is the final transfer function of the given state space model. So that is it, guys. So I'll just briefly go through the lecture and discuss what we have seen in this lecture. So go back to maybe slide number 1 and quickly just recap the whole lecture in a couple of minutes. So in this lecture, what we have done is first of all we looked at what we discussed last time. So we briefly revised the lecture number, the contents, the important contents of lecture number 3. So details of these contents is of course available in lecture number 3. And then state space model, we looked at state space model. Its essence is basically the introduction of the internal or state variables of the system. This is the definition for any number of variables to qualify as a state vector. The information combined with the information of the input should be enough to uniquely determine the output. and then d is usually 0, y is usually x1 or some other state variable. Then we looked at the example of how to convert the state transfer function or differential equation into state space. We have 3 steps: define the state variables, derive the dynamics, and write the model in matrix form. We defined the state variables: x1 is equal to y, x2 is equal to y dot, x3 is equal to y double dot, and then we derived the dynamics, and then we write down in the matrix form. That was it. But then we looked at an example where we have u dot involved, and in order to deal with that, we have 2 extra steps where we decompose the system into series of 2 transfer functions. We derive the transfer function and the state space for this part, and then we add the equation of the output using this part, and then we have our state space model. We write it in the matrix form, and then we look at the general form, how the coefficients are related, and how you can convert state space into transfer function. And then we looked at the example in a animated way, like where the coefficients are placed in each of the LTI model types. Then we look at another example and another example, and then we looked at how the formula for conversion of state space to transfer function is derived using the Laplace transform under zero initial conditions. And then the example of that, which involved some calculations, the inverse of a matrix, and then some multiplications. It is tedious, but it's straightforward, at least at your level, if you know how to calculate the inverse of 2 cross 2 or 3 cross 3 matrix. If the state space matrix is larger, like 4 cross 4 or 5 cross 5, then that's a big problem. But thankfully we have MATLAB, so we have some MATLAB commands involved. For example, SS to TF and TF to SS. I encourage you to look at these MATLAB commands. So for example, let me write them here. So in MATLAB there is command SS to TF, and there is command TF to SS. Just go to the MATLAB, type help or doc. So help SS to TF or help TF to SS. You will find those commands, and those are really useful for converting state space to transfer function or transfer function to state space. That is all for now. Thank you for listening, and stay tuned for lecture number